So before I will continue, I'll just say a couple of words of connection between what I will present and what Renato presented in this last talk. So you remember that there was some conditional entropy, and also there was in his talk there was no Hamiltonian, right? So the systems, all the systems he considered had trivial Hamiltonians. The energy came only through this Landauer principle. And so this, in the language I proposed, so this belongs to this thermo for kids, but it's not so kiddish because I presented within this subject, I presented just the two simplest results, which involved two quantities, H max, and H min, but not conditional. And that was the amount of work I can draw. That was the amount of work I need to put to form the system. While here you have conditional entropy. Why? Because Renato considered the case of drawing work, but if you may have your device may have some correlations with the system from which you want to use to draw work. So in my case, this system was not correlated with this, and therefore it was just A max on my lecture. So and also let me say this. So Renato said that from this quantum information techniques, you can try to answer the questions which is really the formula for the entropy, and why is it like that? So as he argued, we thought that we are used to the von Neumann entropy or the Shannon entropy in thermodynamics, but you can. It turns out that this is true for independent systems, and then if you have more general situation, then you can ask what is really the entropy, and he said, well, in most scenarios, this is the entropy is a relative. It is a conditional H max. So in this now, and now I will talk about thermo for adults, and here is even a newer twist. So it turns out that when you ask what is the true entropy, the answer is that you cannot state it by means of entropy. You need relative entropy, right? So in standard thermodynamics, somehow it happens, and you will see how, that this relative entropy actually gives rise just to entropy, and that's enough. While in most general scenario, you will need a really relative entropy, and the relative entropy will be with respect to a Gibbs state which will contain Hamiltonian. Here you have no Hamiltonian, we will have Hamiltonian. The Hamiltonian will be in this, will be here. So let's say this will be the Gibbs state that will depend on the Hamiltonian. This will be the system with this Hamiltonian. Here will be the Gibbs state. So yeah.
This is notation. This is like a relative entropy.
So you like S?
No, but this is yes, it's just a notation.
You want S?
For conditional entropy.
Oh yes.
Whether it's one vowel.
Then when I say D, it is relative entropy. When it's just H, then it is conditional. Can it be like that? Because sometimes people put 2, but I may keep forgetting to put 2. So just the D will be the relative entropy, like at some distance. I don't know why it's D, but maybe it's because. Right. So what I promised on the last lecture, I promised to state and prove condition for transition. Oh, sorry. Usually I put here rho. Under thermal operations, and one maybe So I said what are thermal operations. So thermal operations are such that I can add arbitrary system in Gibbs state, apply unitary commuting with total Hamiltonian, and remove systems. I was also talking about the heat buff, but heat buff can be one of these Gibbs states that I can add. Why I talk about this heat buff separately? Because when we want to prove some results about this, it's good to have some nice Gibbs state that you add, and perhaps also universal. That is for any states it will be the same. So it's good to have heat buff in mind, and also it's mostly for this reason. So essentially that's thermal operations, and now we ask this question, and I say that I also said that if we answer this question, then we can we also define work in terms of state change. So if we know what's general state to state change, then also we can answer all questions: how much work I can draw, how much work I need to put. So we'll be able to ask these thermodynamical questions, answer these thermodynamical questions. So good. So let me first state the result. So the nice answer is if these are diagonal in energy basis. There are partial answers if they are not. So I will concentrate on this simple case, and maybe later we'll say what we know if they do not commute with the Hamiltonian. So we need a notion of how to call it, thermal diagrams. So simply to state rho. So I will, unless I will say rho and sigma commute with H. So to a state rho, we ascribe a function that acts on from z 0 to z to 0, 1, where z is the partition function. So it's just for okay, where this labels also degeneracies. So I can or I can do this. Okay, so that's the partition function. So we ascribe a function. How this function is built, how it's constructed. So we'll define below. We'll define f. So how it's constructed. So we take we consider p probability. So as I said, this state commutes with H. So I can represent it by means of just probabilities. So we have a probability of given energy. And we have I can label the eigenvalues of rho by energy and by the index that runs through degeneracies, right? So let me write. So rho is equal to sum over g over e g e. P of E EGE. Good. So we consider this set of probabilities that eigenvalues of rho, and then we rescale them. How we scale? By multiplying with the Gibbs factor, Boltzmann factor. That's the rescaled values. Then we order these rescaled values. So that's first rescale, then order. Order rescaled values. So we simply take some such energy maybe for the, in order not to die out of too many indices, let's assume that rho is non-degenerate, just for simplicity, because this may be a cloud that will hide simplicity. Let rho be non-degenerate. Okay, so from rho I remove these now degeneracies. Just to see how it works. Right. So we have this. So we order them decreasingly, which is we do this, and so on until this some f. So suppose this is some of sum over E, and there is k energies. Right. So we order them. So this you may recall majorization in this term for kids, where we need to order probabilities. Now, suppose that you have trivial Hamiltonian, then these factors are all equal, and therefore this ordering will be precisely ordering needed for majorization. Will be just ordering of these probabilities. Now, because if this is non-trivial, then this may be different ordering. Okay. So this is so this we call beta ordering. So it's ordering relative to this Boltzmann rescaling, and okay, once we have this, we can define function f. So f is linear interpolation between the following points. So simply we take on the x-axis we take this, and on the y-axis we put these. So this is one point, and then you have ik. So how this function looks like? It looks like partially linear so here we put these sorry, it's a mistake. Sums, it should be sums, so I cannot write it so easily. Maybe I will draw it. So here I don't have too much room, so yeah, I will draw it here, and here I will write. So of between which points? So first we put this. Okay. And then sum of minus of I1 plus I2, and here sum of these guys plus P of E I2, and so on. So right, so the diagram looks like that. So you put just this first stuff. Here you put, say, second. okay, third, and so on. And finally, look, this adds up to z. So finally we have z. Z is sum of these. And then here we have 1. So here we put this. Now let me first draw it and then. No. So it's always convex. This is good. So here is, say, PE1. Here you have PE1 plus. Let's put like that. Yes. Here is PE1. Here is PE1, E2, and so on. Good. So this thing is a function that is ascribed to rho. While this thing is also a function, and this is a function of what state? Gibbs. This is a Gibbs. So the Gibbs state. Why? Because for Gibbs state you simply, this is simply the same, but this is normalized, and that's why here we have z, and here we have just 1. So the ratio is always the same. So the ratio is just 1 over z. So that's a Gibbs state, right? And now if we have such to every state, so we ascribe this function, we can because this beta ordering, this angle it always goes down. So the function is convex, and now I can state the result. So which is thermomajorization. Oh, let me define thermomajorization. So one state thermomajorize or beta majorize the other if and only if the function of rho is always greater than the function of sigma. So we, for example, see that any state thermomajorize the Gibbs state. So this is the generalization of majorization, and if you go to the books, there are books about this. It's relative majorization. And also, I like sayings of Robert Alitsky, so let me say two. So one saying is that everything is in journals. So it's really hard to discover something new. And indeed, these things were in some form present already in the 70s in relation to thermodynamics. So essentially, and the other saying of Robert is that the science is being developed like this. So you simply start from here, you make a big way, and finally you discover something completely new that turns out to be a little bit just from here, right? So, but it's like in Hegel philosophy, it's after the history. So you are in the same point, but you really know more now. You know, after the history, you are more. So yeah, so this is how also this developed. So finally, after we did all this, we found that we are a little bit of some 70s papers. I think we had a closed nice thing. So there were some maybe partial stuff, but I think that the one thing that is like I believe completely new is the definition of work, and then we can exploit it. But otherwise, you can I also haven't seen these diagrams, but they should be somewhere. So if you yeah, you can cook up some forms, but they are not more informative but by saying this. So for example, and this later paper by Egloff and others, they wanted to have an expression, so they cooked up one. Okay, it's really not much more than saying this. Yeah, that po prostu you take this point and you interpolate them by linear functions. So it's piecewise linear function, and each piece is between these two subsequent points.
Is the P related to rho?
P? Yes, exactly. P is the eigenvalues of rho. Right. Yeah. Good. So good. So now there is the result. One can go from rho to so sigma if and only if rho thermomajorizes sigma. So now when we know it, you could recover this fact from actually two separate researches. So from the 70s papers by by essentially this is the main name. There was also a paper with Mead, and so that's 70s, and 2000 by Yanting et al. This paper that appeared too early, and only now I think it's properly recognized and used. So from these two papers, you can get this. Well, I would say yes.
Do we allow this different age for rho?
This we can. We have a way to do that. I should come back to this. For simplicity, for y, I assume this is the same. Maybe quickly I say that in this paradigm, you can add arbitrary Gibbs states. So you can say add some system in H prime and then remove your system with H, and then you should consider the transition from rho H plus your ancilla, your rho H prime, to something you don't care here, sigma H prime. So that's one possible way of thinking that I change Hamiltonian. But this is more suitable to this result theory, but we also devise some way which is very like in thermodynamics where you change Hamiltonian, but that's for later. So this is just yes.
Do you have maybe an example when you know if two states are thermal, that you can move from one to another, but which you don't know how to do it efficiently? A multi-particle state?
This is a single system essentially, and a heat bath
Yeah, you can think of multi-particle
system.
in the same.
No, I didn't think about it. How to do that efficiently? So the way we construct an explicit transformation that does it, but that's very microscopic transformations. In some cases, you really get that it can be very crude, and it is just changing Hamiltonian in some way. So some really, like in thermodynamics, like you move the piston, so by some small changes of the Hamiltonian. But then for this, I don't know how to translate it again into some complexity of some multi-many body systems. So maybe later I will also tell how to do that in a more crude way. But for a while, I will present a transformation going from here to there that is like extremely microscopic. It looks at single levels of the heat bath, even this big heat bath, not only of the system. So good. It's actually fun that essentially it looks like there's no difference if you just change Hamiltonian of your system, which is very crude, and only interact with the environment with a heat bath via some, say, weak coupling. And the situation where you have like extremely good resolution where you see whole heat bath and you address every single momentum, every single particle. It doesn't really change anything. It's for drawing, for extracting work. For other transformations, it's still in the progress. We don't know how it's related. Right. So it's this. So let me give it some quick some examples of how this. Of how this thermomajorization work. So I consider two-level systems. That's a qubit, and we see from what qubit we can go to what other qubit. So two-level system. Good. So let's draw this diagram. So for two-level system, we can consider we have essentially two kinds of beta orderings. So suppose we have a state that is more ground than excited. Okay, it has it's almost ground. Then the diagram will be what? So let it be less excited, or let it be less excited than Gibbs. Okay, so it means that the probability of being excited and probability of being ground, the probability of being excited is less than the probability of Gibbs state to be excited, which I denote by R, and this is simply E2 minus beta energy, what was upper energy divided by Z. Right. So suppose this is less excited than Gibbs state, then look at this. No, then what? Then we want to see what's the term beta order. So we multiply our probability. So our state is this. Our state is this. P excited, and being a state P ground, and being in a ground state. And then we want to make beta ordering, so we multiply this times E2 beta E excited. Okay, and we want to see what's the sign. We want to compare this with the ground and E2 beta E ground, right? So what's this? So we say it should be less excited than Gibbs, so which means what? Aha, which means that this, so we have on one hand this thing, and then it's therefore more ground, so this is greater than R ground, which is this thing, E2 minus beta E ground. So then we take the ratio of these. So from these two, I guess, we get that the ratio of, now I change notation, ratio of ground to excited is, I have here that it is greater than this thing. Let's check it. Is that true? I take this. This is greater than this. And this thing is smaller than this. So this ratio will be greater than this thing. Z will be cancelled, right? So you see from this that P excited times good. Divided. So I from this I get what, that P excited. I multiply this, and now it will be this is less than P ground times E ground. Is that true? Yeah. So we have this thing. So you see that in this case, this beta ordering is the same as our standard ordering, because this P excited is also itself less than P ground, right? So then beta ordering same as standard ordering. Okay. And so the diagram then looks like what? Since this is the larger thing, so I should put it first. This I put here E2 minus beta EG. EG is larger, so E2 minus is smaller. So interesting. There's something different here. so I will put here first. So I will put here first E2 minus beta EG. It's ground. Good. This is ground. So ground edge is small. So this will be big. Perfect. Big. Okay, and here you have E2 minus beta E excited. So and this P excited is also a So here I first take P ground, which is big, and here I put I have just one because it's P ground, right? This is P ground. This is P excited. So then I get something like maybe something like that. Okay, right. So then you see that this is big, and also this is big, this is big. Okay, good. So now consider a state which is so that was state less excited than Gibbs. So now we consider a state which is more excited. Now consider more excited than Gibbs. Okay, so this is this picture. Actually, it need not be more excited, yes? It's just only need to be more excited than Gibbs. So it can be still, look, it can be still, like the upper level can be less, have less of population than this, than lower. But it should be more excited than Gibbs, just this thing. So then you will get what? That now the beta ordering will be opposite. And first you would have E2 minus beta E E E excited, and here you will have P excited, and here's one. Yeah, so you'll have something like this. Right. So you have two kinds of different beta orderings. This is same, but this is different than standard majorization. So here, let me write. So here, P excited is I wanted to no, it's good. It's good to. It's a pity that because I wanted to show an example where you have beta ordering is different than standard ordering. So I would like to, yeah, it's good, it's okay. So this is standard ordering. So according to standard ordering, you have this, but according to beta ordering, you have this. Right, so they are now different, good. So when the state, so now so that's about single diagram. Now we want to apply this result and want to see how you can, when you can go from one state to the other. So we should have two states. For each we should draw the diagram, the function, and we should see what how the functions are related. So we take rho sigma, and let's assume first that they have the same beta ordering. They have same beta ordering. This means that suppose it is this kind of beta ordering, then it means that both of them they have this kink above this point. Beta EG E2 minus beta EE. So then you have so then you have, say, this is, say, one state, and this is some, for example, some other state. Okay. So then here you have like linear order. So every two states they yeah, you have linear order. It's very easy to decide when your state major as the other, because these points are just exactly on top of each other, so you can just check whether this point is above this, and that's the end of the story. So, for example, so you can go from, you cannot go up, you can only go down. So if you have some rho, some sigma, and also this white, let it be some I don't know, pi. So you can go from sigma to pi, and you can go from rho to pi, and you can go from rho to sigma, and finally you can go to the Gibbs state. Right. So now, if you have different beta ordering, then the criterion is not so easy. It's simply you have to compare these two functions, or you have to look at the diagrams. So mathematically, you just have to check point by point, but graphically, you can also see it graphically what to do. So we now suppose that one state has this beta ordering, so it will be something like this, and the other state will be will have the other beta ordering. So now these two states are not comparable. This is one example, and the other example is when they are. So you simply have, and for example, you may have this, and then further. Right. So here you have both situations. Rho and sigma have different beta ordering, but here rho cannot go to sigma to the sigma. Okay. And sigma cannot go to rho. Sigma cannot go to rho. But here you can go from sigma to rho. From rho to sigma. From rho to sigma. Good. So that's how the criterion work. If you have more complicated states, you have to check whether the functions one above the other. Also, it's maybe instructive to distinguish two interesting different situations. One is just one is this and one is this, but from a different point of view. Namely, let me draw just levels, just energy levels of 2 qubits state. Populations. So I'll draw populations. So it will not be a diagram of this sort, but just we'll draw populations. So here I will just put 2 levels. Here is just 1/2. So that would be a maximally mixed state. Max mix. Okay? P1 equals P2 equal half. Then let me put here Gibbs state. So Gibbs state will be something. So for some non-trivial Hamiltonian, it will have some, say, lower probability of being excited, and larger probability of being ground. So that's Gibbs. So Rx, this is just Gibbs. Okay, and now this situation, it will be either going from some. So now I write. I have this red. I have this red, which is a. I guess it will. Up to some obvious mistake, I will try to say how it looks like. So. So if you have a state which is like this, yes, then you can. the result tells that you can go closer to the Gibbs state, right? So this state is almost ground. Oh, sorry, it's almost what? Almost a let it be almost ground. So this is a probability of being ground, probability of being exact, and you can make it a little bit more excited, provided you do not cross this. So you can, from this direction, you can always go. So that diagram shows that you can go towards Gibbs state, but you can also a different thing is possible. So here you do not change this ratio. So you have this is has probability of being excited less than probability of being ground, and the state has the same feature. Its probability of being excited is less than probability of being ground. So they have the same feature like this Gibbs. Probability of excited is lower than probability of being ground. But you can also do make a transition which is not like that, namely which is from this red, you can also go to something like here. Okay, so this now this is look, this is less. So this state is more ground than Gibbs, but this is less ground than Gibbs. So or this state is more excited. Sorry, this is less excited than Gibbs, and this is more excited. So let me write. So this state more excited than Gibbs, and this red, the red one, is less excited than Gibbs, right? So you can also make this. You can also make this transition, right? And this is completely different kind of transitions. And when we will try to do it by means of some more crude operations, it means that with this we'll have problem. And with this, it's okay. But in terms of our thermal operations, both are possible. Good. So that was these were example how it works. And now let me try to sketch the proof of this result. Okay. Namely, so how we do that? So it is very convenient to have indeed now some big heat buff of some properties. These properties you can prove from. You could use many copies of some Gibbs state, and it will have some properties. But I will not derive it. I will just assume the properties, and then we'll use them. And I will not show the derivation. There was one exercise that is related to this derivation. So proof sketch of this result of thermomajorization criterion. So how we do? We start with some heat buff that we in our operations we can add whatever heat buff we want. So we'll add some heat buff in the Gibbs state, which will be good for us. And then, so now everything is diagonal, so I can write it by means of, I can just write it by means of separate energy blocks. Okay, and so this is the state that is that's restricted to give a fixed energy block. RS is, so again I will consider non-degenerate state. Just for simplicity, but the heat buff must be degenerate. The degeneracy will be thanks to them we'll be able to make these transformations whenever state will thermomajorize the other. So the thermal buff is, of course, of this form. This G will be different for each energy. It will depend on energy. So how can I write it? I can write it also as in the following way. I can write it like a, maybe right here, as a mixture of what? I can take here this thing. So Gibbs state, the heat bath will be in a Gibbs state, and Gibbs state is maximally mixed on degeneracies. So let me just write it in such a way that it's explicit here. So I multiply here by degeneracies, and here will divide by degeneracies. Rg divided by G of Er. So you see that this thing is a maximally mixed on degeneracies, right? So this is a identity over G Er maximally mixed. Good. So the thermal state is a bunch of these maximal mixed state, and I also want to know something about this term. So right. Okay, but before I say it, let me write what we want to have. So we want to. So this is a state. This is tower, and we want to see what is this. Why we split like that? Because our unitaries can only act within the degeneracies, so they have to commute with the Hamiltonian. Therefore, we will be only able to transform this somehow for each fixed E. So I fixed E and look fix E, okay, and I look, and the question is how this state looks like. How this state looks like, right? So because the energy is fixed, then whenever I have some energy of reservoir and a system, they should add up to the same E. So this will, so maybe this will move. They are too large. Okay. So maybe I'll just okay. Okay. Well, so what we can do is the following. We write this as over all these parts that sum up to E. Okay, and then we say what we have here. If we have any such pair, this system is described by this by this expression, while the tau R is described by the by this expression. So I put here Ig of ER divided by ZR, and here we have identity by G of ER. So these two parts. Now, now we see that this ER and ES are constrained by this. So we write everything by means of just the energy of the total system. So we write E2 minus beta, E minus ES, and times G of, this is the degeneracy of the reservoir, minus ES. Okay, and yes, and then here we have this thing, E minus ES. Okay, now I will need an assumption on a heat bath, which will be that a degeneracy satisfies this formula. Of course, it can be only satisfied through some typical energies, for the energies that are occupied. There are some weird energies that are never occupied, and for them the degeneracy is not relevant. But for these energies that are mostly occupied, we want a heat bath that has this formula, satisfies this formula. So then we can insert it here. Then we can now sum over E and ES. This we rewrite, and here we simply see that we have beta ES times dr of E times E2 minus beta ES by Z, and you have this thing. Right, so we have this cancels, and we see that this is depends only on E. This depends only on E. So we can now finally the full state write as in a very appealing form. So the total state rho tau r times rho as given E. It is this form. So we pick this. That doesn't depend on ES in front, put it in front of the sum, and this will be some probability, but not of the system. It's just probability of essentially of appearing this block E, and here we have sum over. Actually, I think here I should keep this notation. S times 1 over this thing. As beta E S. Right, so that's already very nice. So in every energy block with this probability, we have such a state. Right, we have such a state. It's a normalized state on system reservoir given energy E. So it's good to the total state is essentially times these guys. Right, but my unitary. So essentially, I could write also this. So my unitary can only act within the block. So I can only change these states, and I will consider just only fixed energy and we will show you that you can from here get the state you want, the output state, and then for every energy you will do just the same. So there is a very convenient way of picturizing this situation. Namely, if I fix the energy block E, so this may be I can show you the structure of levels. Structure of levels in and for fixed IE. So it's convenient to draw these levels in the following way. We start with how do we do? So we just write, let ES1 be greater than ES2 and so on, like this. Then what happens? This thing is precisely the dimension of this operator. So this for each ES, this has this many levels. So we have no, let it be. Oh, sorry. What's my notation? My notation is this. So you see that if this is large, then you have not so many levels. So we write just couple of levels, and here is this thing. Then this is for ES equal ES1. Then we have more levels, and then we have more and more. Right? So here is buff. Here is system. Buff and the system, right? So we have such a structure, ES2 and so on. So it makes very good sense. We'll see why. Namely, we'll quickly see that, for example, easily you can go down from an excited state, but you cannot go really too much up from the ground state, which should be in thermodynamics. So so each energy of the system leads to a group of microstate of the heat bath, whose the number is determined by the energy is actually it's proportional to this factor. So the larger energy of the system, the smaller number of the levels. So we can write here that there are D1 of them, there are D2 of them, and so on. And these dimensions for a given energy, there are some D that depends on E times this. Right. So what's the population of these levels? So also we can, since this is just a single level, we equally well, tensoring this some single level times many. It actually is like tensoring with a one-dimensional Hilbert space doesn't change the dimension of Hilbert space. So we can actually forget about these levels. We can just say that this time this is just this level. So so even more useful picture is when we just have, so I can draw such boxes. So these boxes tells you how much room you have. Okay, and in these boxes I have these levels, more and more. Each energy gives rise to a box, but the box is the larger, the smaller is the energy of the system. And what are the populations for this original state? So population of each level, so population of a single level is what? Here it is, what's the population? This is, the population is this probability times this probability. This probability is 1 divided by this, so the population is given by this. And so population is actually proportional to this. Right? Good. So essentially we have maximally mixed states, but with additional weights fixed by the system's probability. So here where the state rho enters. Oh, sorry. Oh, no, can't be. And they must be small. What's wrong here? I don't understand what's wrong here.
Before we go, can I ask a question?
Yeah.
So regarding the red function,
Mm-hmm.
is g of r the same g of r as in the left hand side, or another function just separating e and es?
This?
Yeah, that g which is function of e,
This is the same function.
the
Yes.
same function.
Yeah. But why is it indeed something very wrong? Because this must be tiny, very tiny, these probabilities, and of course they may be like that. Here is something maybe, no, good, they are tiny because of this. Perfect. So it should be this, and that's why we will have this beta ordering, because we ordered just these things. Good. So these probabilities are extremely tiny because of this big, huge thing. The generalities will be extremely huge. But but they are weighted by. So here we see that the original weight will be in additional multiplied by a factor. Good. So that's how looks the structure. So what we'll do now? We'll do some transformations. So that's a single energy block. We'll do some transformations, which in our case will be just permuting some levels. So it will be some classical permutation, and after this permutation, we'll have some joint. So we have some initial state of Rs given E. Then we will permute. We'll get just some out state. So here, unitary. And now we want to go back to the system. So how we do that? We simply sum up these probabilities. So we sum each box, and then we get raw output S given E, and finally raw output S of E, or full total is just mixture, because we do for every single block we have some transformation, which we will make actually will be make it the same. So it's this thing. Yeah. So you just sum up. So look, if you do not do anything, we should just get original state. So if you sum up this, then of course it will give this, because this is a normalized state. So summing up these probabilities will give rise to 1. So we'll have just 1 times PS. This shows that this procedure. This is some check. Sanity check. Okay. Now let me show you how to, an example, how to see that the what state can go to what other state. Again, example will be 2 qubit. Just qubit. Good. Example. Let's just consider such examples. How to go from suppose we want to go from excited state to ground state. So that's on a system. That's state of the system. Can we do this? So we should be able to do that, because from excited state to ground we do not put work. It doesn't cost work, so it should be possible. So how we do? So this is so we write the structure of levels first. That's structure of levels. Now, what levels will be populated? So probability of so we have these probabilities here, PES. These probabilities, maybe I'll here. So this is a probability of P S2 and so on. So here the probability, this probability is, say, probability of excited is what? Is just 1. But this probability of ground is 0. So we have here indeed levels, but they are not populated. While here we have levels, and they are all populated. But now with what is the probability? Is just this. So the probability of these levels is as written here. Here you have the general formula. So simply, here you have maximal mixed state, right? So these probabilities are just each single probability is just the 1 over the dimension of this. So this is a D excited, and this is a maybe I should better to be consistent with my further notation. D2, D1 for some reason. Okay, so you have here. So now what we can do? We want to go to this state. Well, we can only perform some unitary within this space, and it turns out that there is not much more than you can do than for diagonal states than just permuting levels. So okay, so we want be ground, which means that we want to have all population here and not here. So you should put all these strings here and swap with some strings there, right? So we do the so we simply do this, that we swap these levels. So so here D2. Okay, we swap these levels. So now here we have these red ones. These are now empty, not populated, and these are also not populated, right? So look, the final state is not anymore of this form, where here everything was populated, and population was just probability times some 1 over the dimension. Here it also was, but now here this is not uniform, right? But we will trace out. So this is something. There were some questions whether the state of the heat buff can change after this. Yes, of course it can change after my transformations. I couple to the heat buff feels this and will change, but it will be then traced out because I'm interested in the system. So then what I do, I simply trace out. And of course here these are not populated anymore. These are strings that were brought from here. So here P out is 0. Well, and here I just brought all the strings here, so P out is 1. So we obtain that indeed this is after tracing out environment, it is heat buff. It is indeed a ground state. So now let's try to do the converse. Let's try to go from the ground state to excited state. This shouldn't be possible by thermal operations, because that would be clearly give you work. Yeah. These. These are populated, but these are not, because this was initially the system was in an excited state, so this state was not populated. So if you go to
So this is for the total thing, like system plus.
Yeah, this is for the system and environment. So initially you can look like here. So that's the levels of the heat buff. That's a level of the system. Because it is a single one, it's really redundant to write this level. So essentially you could think that here you have probabilities of a heat buff and you have probability of a system. But if it is 0, then you get that essentially these levels are not populated. Right. So that was this probability 1 of the system here and probability 0 of the system here. So that's where they were not populated. Good. So now we go here. We draw. So we start from now ground state. So these are all populated, but these are not. Right. So P as here is equal to 0. Here is equal to 1. Right. So now we want to make it to get it excited, but of course here we have only some fixed number of levels, which is smaller than these. Okay, so we try our best. So we put all possible levels from here to there, and then we have to be unfortunately left still with some populated levels here. So it shows that this is not possible, right? But what you do is you get something the best you can. Yes, so you get or maybe something here, but also something left here, and that's the best you can do. How to see what state I obtained? So here I had D1 levels, or D2 levels. Here I had D1 levels. Here I have D2, D1. So now I sum up these. So I get there are D2 of them. But what was the probability of each of them? So this is maximally mixed. So the probability was 1 over D1, right? And what's here you have a little bit of these. D2 times 0, because they are not populated, times D2 minus D1, times, and now this original population 1 over D1. Right, so we see that it is essentially 1 minus D2, and here is just D2. Good, so, and what emerges is that this, now what are the ratios of these dimensions? So the ratio of the dimensions are governed by this, right? So the ratios will be the ratio of Boltzmann factors. So these Boltzmann factors put us some bound, how much we can excite it. And it prevents us from some, transitions that are forbidden, that should be forbidden if we want to get thermodynamics. So that's somehow what one get. Okay. Yeah. Again, repeat the first part of the sentence.
So allowed thermal operations include like tracing out only if what you trace out is in the Gibbs.
No, remove again everything.
Remove it.
Yeah, remove everything. Right. So in this garbage, there may be something that is not anymore thermal. So if you interact with some heat bath, yes, you will leave some garbage in this heat bath, which is not really equilibrium. But it will. You do not care that heat bath will become a little bit polluted. Yes. Anyway, it will be then spread. But you are interested in what you can do with the system.
But does that mean that you kind of lost some energy?
Yeah, I might. Yes, I might lose. Definitely, if I do some. Not all these operations are. They may be dissipative. Yes.
My confusion is because this permutation of levels is a very kind of quantum mechanical operation. It's not immediately see that it doesn't require any work.
And but here you permute levels that have the same energy, right? You are within the fixed energy subspace, so you do not change energy.
So your assumption is that it can be done without actually any work.
Yes, without
Isn't that argument still true if you have a coupling between system and reservoir? Because it seems like the
So this U.
formation of reservoir levels actually changes the.
Yeah, if I have some always on coupling, then that's difficult. What usually in thermodynamics is that you couple, like you bring your engine to the system, yes, and we assume that you can engineer the coupling the way you want. So we want to be we will be paranoid, and we ask what are ultimate limits for doing. So we consider initially no coupling, and then arbitrary interaction you want, and then this interaction will actually result in unitary that commute with the total Hamiltonian.
Another question.
Hmm?
Our argument assumes that our system Hamiltonian doesn't have any degeneracy because
Yes. No. No, it's not. It doesn't hinge on it. I did it for simplicity in order not to carry too many indices. But yes, you can add a degeneracy in the system, and it also works. In the heat buff. Yes. So this is when we want to prove achievability, that we can do something. Then we pick a proper heat buff. And actually, you can argue that some standard heat buff, if you consider density of states, it should have such properties. But also, if you want to be just only quantum, like doing this in resource theory, then you say, okay, I take a suitable many copies of a Gibbs state, and they will have these degeneracies. Yes. So later, of course, you can ask, well, but what about maybe there are some... Here, it looks a bit funny, because you say, I cannot go from ground state to excited, because I have not too much room here. So, but that was I assume this as the best heat buff that I can have. Yes, I assume it in order to show you that I can make all these transformations. So maybe there's a better heat buff which doesn't have this. No, but later I show that actually, which is easy step, that whatever heat buff, whatever Gibbs state you add, you cannot beat this. You cannot do more. So yeah. So I'm now talking about achievability. What can we do? So this we can do. But we somehow see, because if you believe me that it's also a limitation, then you see that you cannot do much, and it's good, because you cannot go from ground to excited, which would be shouldn't be possible, right? So okay, so now we ask, well, so what we can do in general if I have arbitrary two-level system, and then what I can do with arbitrary two-level system. So right? So what I can do is the following. So now arbitrary initial state of two-level system. So so there was some conference on quantum thermodynamics, including this new stuff, right, into quantum information, and one of the from more quantum information community, if you remember, said, okay, I have in his talk there were a lot of words qubit, and then a person from this good old school of statistical physics said, you introduce so much weird new vocabulary. It's not needed. When you say qubit, what do you mean? You mean two-level system. So after this conference, I tried to say two-level system rather than just qubit, because why to introduce some?
It's okay to say qubit here.
Here, yes. Thanks. Good. Right. So we take arbitrary state. Arbitrary state, well, have some arbitrary two probabilities. So we have some two colors. So here everything is populated, and there also. Or maybe to keep convention, color convention. So everything populated, but we know that these have different probability than this, because the probability. So what's the probability of this? Sorry, the probability of this is 1 over d. So that's dimension d1. Sorry, there was some notation. d2, v1. So it's 1 over d2 times p of the system being excited state, and then we have 1 over d1 times probability of the system being in the ground state. So these are now, I take arbitrary, completely arbitrary. So my state is now completely arbitrary. Right. Still, of course, diagonal. Good. And now what you can do? So we can do, well, some portion of these, we can leave here. Maybe I should. So some portion can go to here. Okay, but some portion can go to here, and then from this, oh sorry. Okay, and then the left has to be here. So I have this some flows. Okay, some flows here, and then finally big flow here. Right, so simply some states, make the transition here, transition up, and the lower level you are you can have some good. So now let me just see what here is happening. So simply let us note that let this number be some number of states that so they went from 2 and they end up with 2 also. So it's from I think somehow in niedobrze. Good. So here we have some number k2 and go to 2. So here we have what? Started from 1 and goes to 2, and then here we have started from 2 goes to 1, and finally started from 1 goes to 1, and we have some obvious relations. So first of all, we see that if these guys come, that this guy and this guy they add up to d2. So we have k 2 is equal to d2. Okay, these are the trivial relations that you see here, yes? 1 to 1 equal to d1. Okay, they you see here, but you also see that, but you also see, okay, that this plus this must be the original thing. So k 2 to 2 and k 2 to 1 is d 2, and k1 to 2 plus k1 to 1 is d1. Good, so we can write in a more general because it will be more visible what is going on. So simply we have in general what we can do. We can, from some original block, we can go in some different directions, right? So if we have original block, so we have sum over j over I, and I go from I to j, is equal to the original dimension. But also now we also can go from many different blocks to this one. So then we this is going from single block. So it should be I go from a single block I, and this is the I. Now here I go two single blocks. So I go sum over I to j and equal to this. Right? So we have these things. Now, what will be the effective transition probability between my states? If I just sum up this, sum up, it turns out that you can quickly check it, that the transition probability for the system will be just given by these things. Divided by the I. So this will be the process that happens to our state. So a state has some original this probability and this, and the output probabilities will be governed by this. So let me say so this says that original that the output, or let's say p out, will be given by j p I j. Oh, sorry, p out from j to I times p input. probability of J. Yes. Right. So this is the process, and you want to see what process is allowed by thermal operations, and it turns out that any process which satisfies this, right? These cases are completely general. Yes, they are arbitrary divisions of this that satisfy the arbitrary case that satisfy these two equations. So in one of these equations, you see simply normalization. You see simply that from which is the normalization. Let me rewrite this in terms of this thing. So these are these K. I have some currents, and this P are transition probability. So we're now relating currents with transition probabilities. So how is that? So this was relating, but now that was relation. Now we simply use the equations. So we do this. Pij. So this is di. Pi to j should be this, and the other is di pi to j should be dj. Okay, here is summation over j. So essentially, so this is actually equivalent to normalization, nothing more. So that's as it should be. It's not so interesting. Must be 1. So this is more interesting. What it means. So you remember that the number of levels here, there, and so on, are related by a Boltzmann factor. So let us use this. So we know that. So what I said is that this di is some d times e2 minus beta ei. Minus or plus? Minus of the system, right? So we insert it. D will get, so we insert now to this equation. So we have this e2 minus beta eis pi j is equal to e2 minus beta ejs. And now you can maybe divide or times d. So you can divide by z if you want. And you can cancel this. So what you get is this. Let's call this qi, ri. It's a probability of a Gibbs state. So ri is a ri. So sum over I. Ri is a Gibbs state. Gibbs state of the system. Oh, well, right. So we do this. Okay, must be equal to. Okay, that was what I wanted to derive. What does it mean? So all transformations which satisfy this are allowed. So what physically it means? An idea? Or physically, it's mathematically, but yeah, it means something mathematically. Yeah. Yes. So this means that thermal operations preserve Gibbs state. So we have realized any transformation. We are able to implement any transformation that satisfies this, that preserve Gibbs state. So we proved. So we prove it that thermal operations can perform any channel, or sorry, any transformation that preserve Gibbs state. Okay, now you this.
Isn't that the direct consequence of our assumption, actually, where the degeneracy is actually proportional to the e to the negative beta energy system? I mean, that if you want to extract some physical meaning out of it, that's exactly this, I think. Right? So it's like not like driving this equation. It's actually assumptions.
Well, if you wish, yeah, it can be. You can pull it back to this assumption, yeah. But with this assumption, of course, is you can realize. So essentially, it proves this. Yeah. So you may be right that to prove this, you need to pick up a proper heat buff, which has this. It satisfies the assumption.
Then what's the physical implication or the intuition behind our assumption at the beginning?
So I can tell you how we derived it. Yes. So it just started from just many copies of a Gibbs state, and we realized that it satisfies this. Then we said, but it's so nicely physical, it must mean something. So then we cooked up a non-mathematical, but a derivation that is good for textbooks, where we quickly derive it by just defining S or S just logarithm S of E as a logarithm of the degeneracy. Then we define that beta is d di S di E, and we require that beta is constant. And then from these two things, you get it. So basing on this, we say this should be also not only something particular for raw tensor n for many copies of a Gibbs state, but also for just some generic heat buff, essentially for some ideal gas or something, so it's much more than just tensor copies many copies of a Gibbs state, which would be very quantum information, but maybe not very appealing for physicists. Right. So good. So we proved that thermal can implement this. Now we can ask, well, but can we do more by thermal operations? So the answer is, of course, no. We cannot do more, and the proof is trivial. Thermal operations was adding Gibbs states and using unitary that commutes with Hamiltonian. So if we start with a Gibbs state, if you add any other Gibbs state, then everything is again a Gibbs state. And then if you apply unitary that commutes with the Hamiltonian, then of course it commutes also with the total state and doesn't change it. So that's one thing. And the other thing, by definition, almost by definition, almost by definition, thermal operations have to preserve Gibbs state. Good. So we have a characterization, and as I told you, after we found it, then people said, okay, now we can take this 70 years paper and the Yancing paper put together, and we get it immediately. Yes, that's true. So essentially, but not this way. So I say I like this picture because it also shows you really what kind of unitary you need to do in order to implement given transformation. You can really point it out, and you can then analyze it. Good. So that's this thing. And now but I still am far away. How much time? Just end.
0.
0. It was very good time. Very, very good point. Yes. Thank you very much.